Some setups benefit from a two-stage chuck tightening process. If you do that, don't forget that second stage, or, the cutter might push the material off the tailstock and right into your heart. No, that's not a romantic metaphor, like you could die. Hello Internet, my name is Quinn, and this is Blondihacks. It's an exciting day here on the Pennsylvania A3 switcher because I'm going to make the final detail pieces on this tender. This is the last thing I have to do before it's time for paint. That's super exciting. It's been a long road to get here. Let's get into it. On the front corners of the locomotive and the rear corners of the tender, you can see there's vertical poles that have kind of a decorative shape to them. They're handholds for the crew when they're standing on the footboards. And those are what we're going to be building today. It's fairly difficult to find these still on the locomotive in photos. You can see the ones on this locomotive are bent, which tells you they have a hard life. In fact, this is the only photo of the A3 I could find where these poles are still there. They are mostly gone. This is Kozo's interpretation of the shape of those poles. Very good photos of these types of details are hard to get, so this is what he designed and it's what we're going to build. I'm going to use this 316 stainless bar stock that I found in my bins to make these guys out of. They're going to remain unpainted, hence the stainless. I'm going to start by making the threaded and hexagonal section at the bottom of each pole. I start by facing off the end, as is tradition, and I'm going to turn the base down to a number 832 thread. The drawing actually calls for an 836 thread, which is a very unusual thread. I'm not sure why Kozo chose that beyond perhaps an unfamiliarity with which imperial threads are common and which are not. The A3 was very clearly designed in metric because, of course, Kozo does everything in metric and converted to imperial, probably in order to sell more of the books in North America. So there's a few places like this where I've substituted his thread choices for ones that are just as good structurally and a lot more common. He also uses a lot of 164 threads, whereas 172 is the much more common thread pitch on that size. I finish up this step by putting the thread on there with a die. Stainless makes really nice threads. It takes a thread extremely well and the resulting threads are very strong. One of the nicer things to do in stainless. Then we do an undercut at the base of this thread. That's going to ensure that when we thread this into the bolsters on the locomotive, that the hexagonal profile above this is going to sit firmly down against the bolster. And we're not going to have any annoying little gap where the threads won't seat all the way down in the hole. So I took all four parts to this stage. Now I'm going to move on to creating the hexagonal profile. For that though, I'm going to need a way to hold this thing in the mill. This round bar that I'm using is a slightly unusual size for which I don't have a collet. So I grabbed a piece of aluminum out of the scrap bin, and I'm going to make a quick adapter collet that will allow me to hold this stuff in a collet block on the mill. If you're a regular viewer, this is something you will have seen me do quite a bit, especially on this project. It's a technique that works really well for me. I turn down the OD to something standard that I have a collet for, and then I drill out the center with usually a drill, because if it's an odd size, then I don't have a reamer for it either. But, drills come in every size pretty much, so you can probably find a drill that's the same size or very close to the stock that you want to hold. In this case, I did have a drill just the right size, so I got a really nice fit on that. Then, of course, I can part this off. The length of this doesn't matter a whole lot. It's going in a 5C collet, and 5C collets actually only grip right at the front edge. So, I made it some arbitrary length, but again, the length doesn't matter as much as people tend to think it does who don't understand how 5C collets grip. And Yahtzee. Then I took this over to the bench, used my fret saw, cut a fine slit in it all the way through on one side, and we're ready to use this. I've got my hex collet block set up in the mill because of course we're cutting a hex profile, so I can feed the stock into my adapter collet, and then I line up the slit in the adapter collet with the slit in the main 5C collet. Any of the three will do, and that ensures that when I clamp down on the 5C, it's going to compress that adapter ring. And that works very, very well. That is not going anywhere. But now how much to cut? Well, the Engineer's Black Book has a great chart for this purpose. If you know the across flats distance of the hexagonal profile you want to create, which is usually the distance you have from a drawing, you can look that up in the chart, and it will give you the H dimension, which is the distance across the corners. That's your minimum round stock diameter that you have to start with in order to get the across flats distance that you want. And then it gives you all the numbers there, so you can divide that by 2, and you know how much to remove on each side of the hex in order to end up with the final profile. Very, very simple. Of course, you can do the math, the formulas are there as well, but charts like this, machinists love them because they just really speed up your life. A quick edge find will allow me to set the height of my hex area on the pole, and then I touch off on the top of the round stock, zero my quill DRO, and then machine down to the depth I got from the black book from here. Doesn't look like much of a cut, but it'll all come together as you see. Now I can rotate the hex profile of the collet block to the next side, making sure to always line up the front edge of that collet block the same way relative to the fixed jaw so we don't lose the edge found position for the height of the hex profile area. And then I run it through and do another cut. And this is all already set up on Z. Because this cut is light enough that I can do it in one pass, this goes extremely quickly. I run the cutter through, rotate to the next side on the collet block, run the cutter through again, etc. I don't have to adjust anything on the mill between each cut, so this goes extremely quickly. Which is nice because I do have 4 of these to do after all. Collet blocks are really fun and very, very quick to set up and use. After running through that process 6 times, there's our beautiful little hex profile. You can see how the corners of that hex land right on the round bar that we started with. And that's how you know you did the math right on creating the hexagonal profile. Now things get interesting though. We've got this whole tapered section with a little bead detail above the hex profile. That's what we're going to tackle next, and this is really where the meat of the challenge is on this part. I'm going to start by turning this collar area right above the hex. That's the largest diameter of the rest of this part. So I'm going to turn the whole thing down to that. I'm going to do that in the lathe, of course, and I'm going to grip on the hexagonal profile that we created. It's an easy way to grip the part in the 3-jaw. You can see I've already put centers in the ends of the parts, and I've got the 3-jaw lightly gripping, and then I put the center in and give it a spin by hand, and that helps get everything concentric. And then I can snug down the 3-jaw. That allows everything to kind of self-align because I'm gripping on a hexagonal profile that should be concentric, but I'm in a 3-jaw and I've moved the parts, so concentricity's been lost. This helps regain some of that concentricity so that it's spinning reasonably well. Now these are decorative parts, so concentricity is not super critical, but that technique, gives us the best chance at making nice looking parts, I think. Machining 316 stainless can be tricky. It's not necessarily the best choice sometimes, but this stuff is actually cutting pretty well, so far so good. So with everything turned down to that collar diameter now, we can move on to the tapered area with that bead detail. For this, I'm going to try something you've seen me do before. I did this in my generator series. I 3D printed the profile that I want to create, and I'm going to use that as a template for the tracing attachment in the Tornado. The Tornado is a hand-turning system for metal created by Eccentric Engineering. Fellow named Gary out there in Australia, awesome dude. One of its best features is this 4-bar linkage attachment, which creates parallel motion and allows you to trace a profile. The Tornado does require me to use my collet chuck for clearance. That means I can no longer use the hex profile to hold onto the stock. So instead I put a piece of scrap in a collet and I drilled and tapped a hole, and I'm going to hold these pieces by the threaded end. Holding a piece by threads like that is not the best for concentricity, but again, these are decorative parts, so it'll be good enough. But you will see a bit of concentricity loss when these parts are spinning. Now that collar detail that we just turned is going to be my reference for setting the tracing profile on the Tornado. I can set the pointer depth-wise on that diameter and the X position using the very edge of where that collar needs to stop. And that collar is in my template as well on the 3D print. So I can line the two up essentially with the pointer just touching the stock, and I know I'm going to be in the right place to start tracing. I also need this template to be straight, aligned with the axis of the lathe, because this is quite a thin profile, so we need to be reasonably accurate with the alignment of the tracer. I did this by indicating in the back of the 3D print, and this worked okay. My 15-year-old FDM printer is not the most accurate thing in the world, but I was able to get it to within 5/1000ths, and that's going to be close enough for this. Now in principle, I should be able to start cutting, and that pointer is going to follow the 3D printed profile, and we're going to be left with the perfect profile. Now, I say in principle because I've never tried the Tornado in stainless before. Stainless is not easy stuff to cut, especially by hand with a handheld tool like this. So I really had no idea if this was going to work. If this was brass, I can tell you it 100% absolutely would have worked because I've done lots of this type of technique in brass with the Tornado. However, the Tornado is really not designed for stainless. Even free cutting steels can be a challenge. And sure enough, after a few passes, I was into the weeds, the cuts were getting worse and worse, and I just couldn't make any reasonable progress, so I had to abandon this idea, and I'm going to go back to more traditional methods. Instead, I laid out where the bead detail needs to go with some dividers, and I've got my compound set at 1 degree, which is half the angle on the final taper we want, and I'm turning this taper with my compound. Fortunately, I hadn't done any real damage with the tornado attempt, so I didn't have to scrap this first part. I was able to finish the taper turning with my compound, and everything came out great. I'm using my tangential tool holder at an angle, which allows me to cut equally well in both directions. That's quite helpful in a situation like this where I'm trying to taper cut up to some scribe lines. Now for the little section above the bead detail, you might be wondering, how do you maintain the taper after skipping over a feature in the middle? The secret to doing that is that I'm not feeding with the carriage at all during this entire cut. All of my feeding on X is only done on the compound. So once you skip over the bead detail, as long as you go into the same depth on your cross slide and only feed with the compound, it's just going to continue that taper on the other side of the bead. If you touch your carriage at all during this, everything is lost. So you have to have enough compound travel to do the entire part on both sides of the bead detail. That V-shaped tool leaves me with chamfers on either side of the bead detail area, which I need to eliminate. So I bring in a grooving tool set aligned with the surface of the 2 degree taper, and I square up the edges of that area and also bring them down to the correct width. To create the half circle shape of this bead area, I'm going to try using a form tool. This is a little bit of a bold move in stainless, but I think I can get away with it because of how small it is and how close we are to the tail support. But before I cut, let me show you how I made that tool. I'm over here on the mill. I've got the hex collet block in there just because it was in there from before, and it doesn't matter what shape the collet block is in this case. And I've got a piece of 01 tool steel in the form of a annealed drill rod. So I'm going to cut my profile in this tool, and then we're going to harden it. I start by facing off the end, which gives me a nice square end, but also just tells me where the tool is relative to the work. It's a little quicker than edge finding in some cases. Now I can translate over and create a flat spot of the desired width. I'm actually going to cut away half of this material. This is a stationary tool, so it doesn't actually matter if the cutting edge is on center on the tool because you can of course adjust the height in the lathe. If this was a spinning tool though, it's critical that you cut exactly halfway through the stock. So it's always just kind of a good habit to split a round blank when creating a tool, even if it's a stationary tool and doesn't actually matter that much. After the split cut, I'm going to flip the part 180 degrees and I'm going to thin it out a little bit. This tool is very small and it doesn't need a whole lot of support, and the thinner it is, the easier the final shaping steps are going to be, as you'll see. So I just removed a little bit from the underside of the tool. Not too much, we do need some strength in the tool of course, but again, the thinner this is, the easier our life is going to be in a minute. Now I set the tool up at 10 degrees, and this is going to give us the clearances underneath the cutting edge that make them into cutting edges. Every operation we do in this position is going to automatically get a 10-degree angle underneath it. I lined up a drill the same diameter as the bead detail, kind of eyeballed it in the center, doesn't matter where, just not too close to the leading edge of the tool, and then I'm going to center drill and drill that out. The center drill in this case creates enough of a dimple to where the main drill will mostly track okay. It'll deflect a little bit, but up to about 10 degrees, you don't have to create a flat spot with an end mill first. You can get away with just locating the drill on that center drill. Now to create the half circle shape, I want to split that hole exactly in half, which is easy to do because the spindle is on 0 in the center of that hole right now, and I know how wide my cutter is, so I just have to move the end mill over by the radius of this cutter, and 0 my x-axis there, mill down to that 0, and we will have split that hole perfectly in half. No math, no measuring, no edge finding. Super easy. With that translation move done, now you can see the edge of the cutter is right on center on that hole. So mill down to here and job done. And because we're milling at 10 degrees, the front edge of this tool is going to get a 10-degree clearance under it, making the front edges of it cutting edges. Which in this case they don't actually need to be, as you'll see, but doesn't hurt. A couple of passes then to mill down to 0, and here's our perfect little half circle shape, with most of our tool clearances automatically put in by the angle that we were milling at. However, we're not done yet. Here you can see the nice front edge clearance, of course, and I'll use a gauge pin to show you that at the back of that hole, we do have the 10-degree clearance there, so the back of that hole is a good cutting edge. However, the front edge of that hole is not a good cutting edge. That clearance, because it's a round hole, does not go all the way around. The front edge of the hole, you can see it was square because we can only tilt that drill on one axis. At the front edges of the hole, at 0 on the y-axis, the hole is vertical. We have 0 clearance. From here, the clearance transitions to the full 10 degrees at the back in a sinusoidal relationship because this is a circle. But the front edge is at 0 and everything between the front and the back is somewhere between those two. The perfect shape would actually be a cone underneath this cutting edge because that would create a perfect 10-degree clearance tangent to the surface at every point. That's really difficult to do at a size this small, however, but we can kind of fake it by adding the clearance to the front edge and a little bit back of the front edge just with needle filing. And that's why I thinned out the tool a little bit as well, because we got to do a bunch of filing, and it's a lot easier if the stock is thinner and if we have a flat surface top and bottom to reference. It would be really nice to do this on the die filer, since this is the kind of job that die filers are actually for, creating clearance on dies and other types of tooling, but it's quite a bit too big for this application, I'm afraid. So hand and needle filing it is. I've blued up the inside of that curve. I know you can't see that on camera, but I've sharpied up the inside, and that's going to give me a filing guide. The key is you want to create the taper underneath this cutting edge without touching the cutting edge. You don't want to change the shape of the top surface of the cutter. You just want to create some of that cone underneath the edge. So bluing up the surface and making sure that that blue never goes away in a thin line just under the cutting edge is how you make sure that happens. Using Sharpie as a filing guide is really effective. In combination with good light and a head-mounted magnifier, you can create quite accurate shapes even at this small size. So you can see now I've got a cone shape at the front edge of the hole, and just by nature of filing by hand, I've also created a little bit of increased clearance right behind that front edge. But as long as the front edge isn't 0, if we've got at least a couple of degrees of clearance at the front all the way around to the back, that will allow the tool to get into the work to where the cutting edge at the back can really do its thing. That 10 degrees is going to kick in and it's going to cut well. And most importantly, we haven't altered that half circle shape on the top surface of the tool. This step is not optional. If we hadn't done this, that blunt front edge on the tool would prevent you from ever pushing the tool into the work. It would never start cutting because you can't get past that area where the clearance is 0 to where you have clearance so that it can cut. With the geometry established, now it's time to harden it. Until we harden it, this thing is not going to be a good cutter, especially in stainless. I start by hardening it, which is to say heating it up to what they call cherry red or a reddish orange. Make sure that's glowing in that color for a few seconds, make sure it's fully saturated, and then quench that in oil because this is an oil hardening steel. I recently did a detailed video on heat treating for beginners for making exactly this kind of tooling, so if you're interested in a lot more detail on this, what I'm doing and why, then go check out that video. After hardening, then I clean it up so I can see the color and temper it from the end so that I have good control, and I dunk it in water to ensure that I stop the temper right where I want and I end up with a nice light straw color right at that cutting edge. Then finally, a hone is never a bad idea. I do a little bit on the front edge and on the top surface. Of course, I can't get the stone on the inside of that curve where the tiny hole is, but if you hone the top surface, that's going to help some to make sure that cutting edge is all nice and sharp. This being a round shank tool, I've got a V-groove tool holder. This is the type of tool holder that you would often use for boring bars, that sort of thing. Also good for a tool like this. Now, because it's a round shank tool, we have to make sure the top cutting surface is level. You can do this by eye, just put a scale on it and get down low and eyeball it parallel with the bench. Close enough is good enough here. Next, I have to get the tool height set correct, and this is quite important, especially for a form tool, because it has high tool pressure. The higher the tool pressure, the more critical it is that the cutting edge be right on center on that lathe. So I take my time and line it up well with the tailstock. Okay, here we go. Let's see how this thing does. I start feeding it into the work, and almost immediately we do have a problem. It's cutting well, but the leading edges of that tool are too deep, if you will. They hit the tapered surface before the main part of the curve actually starts cutting. So this is a little bit of a cheat that Kozo has in his design. He shows a full hemisphere on either side of the taper, which really there isn't physical space for that. So I had to take the tool out and grind a little bit off and try again. And I had to do that a couple of times until the remaining circle area was short enough that the curve met in the middle on the part before those front edges of the tool touched the taper. So Kozo's design here is a little bit of a cheat. You can't quite machine it the way he has it drawn, but you can get very, very close. And that actually turned out really nice. I've got a nice little bead detail there. My surface finishes are nothing to write home about on this part. All of this long, thin turning with stainless can be challenging. So I'm going to go ahead and use some cheater paper to clean up some of the tool marks and improve the surface finish a bit. I'm now ready to remove that little section at the end that's just for tail support. Don't want to do this with a parting blade, however, because you don't want to use a parting blade with the tailstock in place, because the tailstock is putting some pressure on the part. So when the parting blade breaks through, it's going to get trapped by the part. And of course, with a part this long and thin, there's no way you could use a parting blade without that tailstock in there. There's no way you'd have the rigidity. So fret saw to the rescue. Hey Quinn, you might be wondering, what's the Sharpie there for? That's what it's there for. I don't like smacking my lathe with saw blades. One down, 3 more to go. Once all 4 parts were brought to this stage, all that's needed is to round over the end of the taper at the top, right where we cut it off with the saw. No precision required there, so I'll do that on the belt sander. Conveniently, these parts have a hexagonal profile that's a perfect fit in my hand drill. So hand drill plus belt sander equals pretty good hemisphere. Finally, to make all the parts look as nice as possible, I ran them over the Scotch-Brite wheel. The Scotch-Brite wheel will put a really nice satin finish on everything, removes all the tool marks, gives everything a nice, even, flat kind of look. You could also polish them with a buffing wheel if you wanted, but, you know, locomotives and their crews work for a living. They're not jewelry, and I find that satin finishes on parts like this are more respectful of that. Chrome and shine are for trailer queens, not real working machinery. Here's a closer look at that final finish. I really like Scotch-Brite wheel finishes on almost all metals, frankly. Alright, well here's all 4 of them. I'm really pleased with how these turned out. These are pretty challenging parts, but it was a fun level of challenge. I got to do a bunch of neat operations, make a custom tool, do some hardening, you know, all kinds of fun stuff. Now let's thread this into the tender and see how they look. The other 2 will go in a drawer to someday be installed on the front of the locomotive. That's going to be a big day. These are really surprisingly sturdy. They look spindly in the drawings, but the actual product is very, very strong. You can certainly imagine the crews hauling themselves up and down off of those poles. And I don't have to worry about someday shearing them off by bumping them while I'm using this locomotive, which is a nice thing. They're very strong. Well, there you go. That's a couple of sturdy handholds for the hardworking crew on this tender. And as I said at the top of the show, these are the final detail pieces on the tender. We've got a mechanical water pump to build yet, but there's now nothing else stopping us from painting this thing. That's going to be a really big deal. Stay tuned for that. Thank you so much for watching. I hope you enjoyed these final pieces, and thanks to my patrons for making all of this video content possible every single week. You all are my personal heroes, and I will see you next time.